Everyone, welcome back, and today let's solve Leetcode problem 1504 titled Count Submatrices with All Ones. So we're given an m by n dimension binary matrix, and we need to simply return the number of submatrices that have all ones. They don't have any zeros. Every single element or cell in that submatrix is just a 1, right? So pretty straightforward problem statement there. So let's go ahead and dive into the examples really quickly here. Example 1, we have a 3 by 3 input matrix here. In this case, it is a perfect square. It doesn't necessarily always have to be, as we see in example 2. But in this case, the reason why we have an output of 13 is because there's 13 unique submatrices that actually do have all ones as elements in them, right? As you can see, that we can just form 6 with 1 by 1 matrices because there's 6 cells that have a 1 in the actual entire matrix. Then we can form these 2 by 2 matrices, and then these 2 by 1 matrices as well, right? There's 1 2 by 2, there's 1 2 by 1 here, 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 and here, and there's a 3 by 1 here. Summing all of those up, we get 6 plus 2 plus 3 plus 1 plus 1 for the actual 1 by 1, 1 by 2, 2 by 1, 2 by 2, and 3 by 1 rectangles in total to get a final value of 13. And in example 2, we have our input matrix to be, in this case, 4 different columns and only 3 rows, and our output would be 24. Why? Again, because there's a total of 24 unique submatrices with all ones. And so for the constraints here, we see that m and n are the dimensions or number of rows and columns, respectively, for the number of our, or rather in our input matrix is going to be between 1 and 150, and we're guaranteed that it is a binary matrix of each cell being either 0 or 1, kind of just confirming what the problem statement told us, and just kind of telling us that, okay, we're always going to have a valid input, which brings us to how we actually solve this problem in the most efficient way possible. Now, we can kind of work out a solution and an answer for the examples and really all general test cases to a certain extent visually by just looking at submatrices and just kind of counting how many unique ones we can form, but there's actually a much more efficient way to solve this in terms of actual code as well. It's actually a really interesting dynamic programming and histogram based problem, if you will, right? So, at first this looks like, okay, it's just a brute force solution. It looks like we have decently, or at least relatively small m and n values for our dimensions of the input. And so, okay, maybe we can just, check every single possible submatrix inside the grid and see if it contains all ones and just return that value after we sum up all the counts, but that would be way too slow, right? We'd get a huge TLE. That would be like a cubic or quadratic solution at best case, which we obviously don't want. We don't want a TLE, and so we have to somehow kind of optimize from a brute force solution. And that's kind of leading to the main observation that we have to make, in the sense that instead of actually brute forcing over all the possible different submatrices that we have, we can use that histogram logic and that kind of building from bottom up, row by row, using that histogram logic again. So that's kind of like the key observation or key trick, if you will, and actually solving this problem, where effectively, instead of actually just going through every single submatrix, we're treating each row in the matrix as the base of a histogram, where each column in that row would store the height of the consecutive ones that end at that row, and then at every row we'd have to actually count how many rectangles we can actually form using the histogram values and the heights consecutively for each column and row, right? So kind of just to quickly discuss the solution structure here, we're going to have a heights array where heights at j would represent the number of consecutive ones in column j that ends at the current row. And if the cell is, of course, 0, we have to then reset that column's height back to 0 and then proceed building from there. And for each row in the matrix, we'd actually update those heights, right? That's what actually, builds that histogram of consecutive ones. And for each row's histogram, we'd have to actually calculate how many submatrices end at that specific row, J, if you will, right? And to actually calculate that value, we'd have to actually use a stack to maintain the indices of bars in increasing order. And while we actually process those bars and values, we'd have to actually calculate the number of rectangles that are possible for each bar and accumulate that total count and sum it up of all the different matrices that we can actually potentially form as our answer. Again, that main observation still sticks of basically counting rectangles in histograms is very similar to the largest rectangle in histogram problem, which is another problem on the site on Leetcode. rather, if you will, right? Basically, instead of only finding the largest in this problem, we're actually counting all the different possible rectangles, and so it's kind of like a summation problem, and that's where that histogram dynamic programming bottom-up part of it kind of comes into play for the solution. So let's go ahead and get into the actual solution here, and now that we've actually discussed kind of like the solution structure. So first thing that we're going to do is just get, like we always do for matrix problems, at least for the most part here, just the dimensions or our m and n input values of our matrix. So I'm literally just going to call them m and n, two corresponding integers, and they're going to be the number of rows and the number of columns in my matrix respectively. So yeah, it's called mat rather than matrix, right? So m is the number of rows and n is the number of columns in the matrix, just storing those in two integers to be able to use it a lot quickly and a lot more easier when actually building our heights and stack arrays, and also just iterating over the input as well, right? Instead of having to actually type rows, the number of rows and columns each time we want to do that, right? Now let's actually also initialize that heights array that we were talking about in the solution structure here. In this case, it's just going to be the number of columns that we actually have, so filled with all zeros, and it's going to be times n, right? And if it's going to have size n, if you will, and it's going to be filled with zeros at the start. That's how we kind of initialize it. Where basically the whole point of this heights array is to actually represent our histogram for each row, and heights at j would just store the number of consecutive ones in the column j up to that point, or so far, if you will. It's kind of a cumulative, right? Now let's also get a result. Effectively what we're going to return. This is like our actual answer, right? The actual number of submatrices, the count of them, if you will, that have all ones. This is what the problem actually wants us to output, right? That's what we're going to return at the very end. So now that we have all the initial variables initialized and all the actual data structures set up, now we have to actually start iterating over our input and building these corresponding data structures and values accordingly. So first, let's just go with a simple outer loop here for I in the range m. This is just to go over all the different possible rows, or iterate row by row, where I would start at 0 and it would go up until m minus 1 to just cover all the different number of rows that we actually do have, or go row by row, if you will, right? Technically the number of columns, rather. Now, the first kind of case here, or even loop, if you will, in this outer loop here, is to go through each column in this row, right? So for every j in the range of n, for every I in the range of m. So basically for each row, we're iterating row by row, we're going for each column in that row, and we're updating the histogram height in that column, right? So for j in the range of n, if matrix, or rather mat, at I comma j at this corresponding, okay, don't want to do that. At this corresponding I comma j value, if it's equal to a 0, that was kind of like the first case that we discussed. We'd have to actually reset it back to a 0. So heights at this corresponding column j would also be just reset back to a 0. If that isn't the case, however, then we have to actually accumulate it or add it by 1 by extending this histogram height for this column j, and so we'd get heights at j, and simply add it by 1 or increment its value by 1, right? Again, main observation, basically really just transforming the problem from a 2D kind of perspective into a series of 1D histogram problems, just to make it easier to work with as we actually store these heights in a one-dimensional array heights, right? Because as you can see, heights only has one dimension. It doesn't have rows and columns. It just has one singular row, right? And the columns would technically just be the indices or column values in this heights matrix, if you will. Now that we have those two cases out of the way, when we're actually building the heights based on the accumulative values, now that we have that actually set up, now let's actually initialize the second part, our processing, if you will, of our input in this solution, and that's going to be the stack and the sum in the row variables and data structures. So the stack is, of course, just going to be initialized as an empty list before we actually process or parse through our matrix again to do anything with that, and we're going to have another variable called sum. I'll try to keep it as intuitive as possible, sum in row, right? It's really exactly what it means in terms of its naming convention. And of course, that's going to be initialized or set up first at 0, right? So the stack is really just going to help us process that histogram in increasing order. And the sum in row variable is just going to keep track of the number of rectangles that end at the current row, right? And I'm just going to call that sum to kind of sum the count of those different rectangles. Now, let's actually begin the second loop, if you will, in this outer loop here, still all in the outer loop, and that's going to be, again, for j in the range of n. but it's just going to be a separate loop in this case instead of actually working on the matrix heights. And so we're still iterating through each column of the histogram, but in this case, it's just in a separate loop in the outer loop, right? So once we actually iterate through each column of this histogram, we'll first start off our count, and that's going to just be 1, right? This count of 1 is kind of like our starting value for our current iteration in this current column, if you will. Now, once we actually initialize our count, this is where we start our key logic or key solution part logic of the solution, right? So it's going to be a while loop here in this iteration, and while the stack is non-null, meaning while the stack still has elements to be able to pop off, and stack at -1 index 0, and I'll explain how these indices actually work in a minute here, while that's still greater than or equal to height at our current index or column j, it's still valid and we can still go further over to the left, meaning we can get h and c, our two indices if you will, and pop them from the stack. So stack.pop. And once we pop h and c from the stack, meaning there were c rectangles with a height of h, we'll have to actually increment or update our sum in row as well by simply subtracting h times c from it, the number of rectangles or heights from it. And once we do that, we then increment our count by c, right? Because again, that's the number of rectangles that have that height at least h, right? So again, this is the key logic here that actually optimizes our code using the stack in increasing order and getting that kind of like that threshold h height value, right? So basically, again, to kind of reiterate how this part of the solution really works, or this while loop really works, effectively, while the stack is non-empty, meaning while stack and it still has elements, and stack at -1 index 0, which means the top of the stack has a height that's greater than or equal to the current height. So while that's the case, while both of those conditions hold true, we continue our while loop. And so in each iteration of this while loop, we'll first pop off each popped element from the stack, or just pop off the topmost element from the stack, and that's going to give us a coordinate pair, if you will, h comma c. I shouldn't say coordinate pair, but just a pair in terms of a tuple, h comma c. And that really just means that there's c rectangles with a height of h. And then we actually have to remove their contribution, if you will, from the sum in row, because those rectangles, we no longer can actually extend them with the new shorter bar. That's kind of like our new threshold. And once we actually do that, we then have to actually also update our sum in row and our count variables accordingly. And so we then merge their counts into count. And the reason why is because the current shorter bar can kind of take over as the new limit or threshold, if you will. Now, once we do that, that's kind of like the second portion of that solution done. Now we just have to actually add the new rectangles that we actually formed by the current bar to sum in row, right? So we just finished that part. So now we actually have to add those rectangles back from the current bar to the sum in row variable. And the way we do that is take sum in row and increment it accordingly. What do we increment it by? It's going to be some quick mathematical formula here. Heights at j times the actual count of the number of rectangles, and then also, of course, append or stack or add to our stack the tuple h and c values, heights at j, the number of rectangles, and of course the count as well, right? So the number of rectangles and the height itself as well for our new HC values for future iterations where we pop off the stack. So effectively here, just to finally reiterate one more time, we're adding the new rectangles that we actually formed by the current bar at column j to sum in row, where heights at j times count, which is give us the number of rectangles that actually end at column j, and then we'd actually push that value, our tuple of length 2, if you will, heights at j and count, onto the stack for our future processing, right? And once we do that, we then have to finally, at the end of the day, or the last line in this outer loop here on line 6, just update our result. And our result, we know, is just going to be added or incremented by, if you will, sum in row. And why is that? Well, because after we actually process this column, we know that we have to actually count all the rectangles that end here, and so we have to add that into our global result variable, right? And so we're basically just adding to our result sum in row as the number of rectangles that end in this specific column. And finally, we then exit the outer loop once we go through all the possible row by row values and just return our result as the count of submatrices with all ones, which is exactly what the problem asks. So unless I made any syntax errors here, this should be accepted and this should be a valid solution. Yeah, so probably just made a quick syntax error here. Just gonna quickly run through my code, make sure I did not. Okay, yeah. Make sure I did not make any syntax errors here, but this definitely is an accepted solution. This does for sure work. I just don't know why I'm getting a slight error at the moment. I might just paste that into the description of this video and give you my actual solution that actually was accepted on Leetcode after. But yeah, just gonna quickly troubleshoot here to see what the issue could potentially be. But feel free to just kind of fast forward this part of the solution. This is just me kind of debugging my faulty code here. Not in terms of logic, but rather just in terms of syntax, if you will. Stack.append heights count. Okay, yeah, so I don't exactly see where the issue is rooted, at least as of now. So this is a little weird. But yeah, this is indeed how you solve the problem here. This is an accepted solution. I'll just paste my actual solution into the description of this video, right? But to kind of reiterate how we actually solve this problem, basically, how we actually built our solution is for each row, we treated that as the base of a histogram, and we just used the heights array to actually store the consecutive ones up to that row. And then we actually did use that stack in increasing order there, where we counted all the rectangles that we could actually form in that specific histogram, and repeated that kind of operation, if you will, for every single row, and accumulated that result in sum in row that we effectively added at the end to our result variable, right? So that's kind of like the main optimization. Instead of just brute forcing all the submatrices directly, we're instead reducing the problem into just multiple different histogram sub-problems, if you will. So our runtime complexity for the solution is going to be big O of m times n, as you may have imagined. M is going to be the number of rows, and n is the number of columns, because for each of the m rows, we process all of the n columns, and every column we push and pop from the stack at most once per row. And so it's still going to be linear in terms of m times n, and the memory or space complexity is really just linear as well, big O of n, because the only like limiting or threshold data structure that we're going to be using is the heights array that we see here, and that's going to have, of course, a size of n as we initialize it to have, and the stack is going to have at most n elements, so n is really our limiting factor, and hence becomes our memory or space complexity as well of big O of n. So if you guys enjoyed this solution and learned something new, please consider liking this video and subscribing to my channel, and without further ado, I will see you guys in the next video. Bye bye.